Did you know that Mars was once considered a world with genuine potential for life, only to decline and transform into the frozen desert we see today? The contrast between ancient Mars and the barren planet that exists now remains one of the greatest unresolved mysteries in planetary science. Across the Martian surface, orbiters and rovers have uncovered ancient valley networks, dried riverbeds, and fan-shaped deltas, geological formations that can only emerge when liquid water flows steadily over long periods of time. So what was early Mars truly like? The evidence suggests a planet that once sustained a wet and dynamic environment for millions of years. Mars was geologically active, continuously reshaped by climate and tectonic processes, with conditions that in many ways resembled those of the young Earth. To understand how Mars became the hostile world it is today, we must travel billions of years into the past, to an era when the red planet was still evolving, changing, and writing the first chapters of its own history. Between roughly 4.1 and 3.7 billion years ago, during the Noachian period, Mars was a radically different world. It was younger, warmer, and far more active than the planet we know now, a place where stable liquid water may have existed across vast regions of the surface. At that time, the Martian core remained intensely hot. Thermodynamic models indicate that its iron and nickel-rich interior had not yet cooled enough to halt convective motion. As a result, Mars possessed a powerful global magnetic field. This invisible shield protected the atmosphere from the solar wind, which in the early solar system was significantly more aggressive than it is today. Volcanic activity occurred on a planetary scale. Massive structures such as the Tharsis region were forming, releasing enormous amounts of carbon dioxide, water vapor, and other volatile gases into the atmosphere. Scientists estimate that atmospheric pressure during the Noachian may have ranged from several hundred millibars to more than 1 bar, dramatically higher than the thin modern atmosphere of Mars, which averages only about 6 millibars, less than 1% of Earth's surface pressure. With a denser atmosphere and warmer average temperatures, a functioning water cycle likely emerged. Rainfall may have fallen across the young basaltic plains. Water collected into streams, carved deep channels through the terrain, and formed rivers, lakes, and possibly even temporary inland seas. This conclusion is based on thousands of geomorphological features identified from orbit. Dense branching valley systems, especially throughout the ancient southern highlands, closely resemble river drainage networks found on Earth. Their shape, depth, and complexity strongly suggest long-term erosion caused by flowing water over extended timescales, potentially hundreds of thousands or even millions of years. Yet even during this so-called golden age of Mars, hidden weaknesses already existed beneath the surface, like a silent countdown no one could yet detect. The Noachian era eventually came to an end, but it left behind a permanent geological archive across the planet's crust. The rocks of Mars preserve a record of its environmental history, one that scientists are still trying to decode. On Mars, minerals act like frozen chemical memories. They preserve information about temperature, water chemistry, acidity, and even the slow planetary changes that unfolded over immense spans of time. One of the most important discoveries of the last 2 decades has been the widespread detection of phyllosilicates, or clay minerals. Spectral observations from the Mars Reconnaissance Orbiter revealed that these clays are concentrated primarily in the oldest terrains, regions dating back more than 3.7 billion years. Chemically, phyllosilicates form only when basaltic rock interacts with liquid water for prolonged periods in neutral or mildly alkaline conditions. On Earth, clays are considered natural catalytic surfaces where organic molecules can accumulate, bond, and undergo increasingly complex reactions. That raises a profound question. If prebiotic chemistry ever had an opportunity to emerge beyond Earth, could ancient Mars have been one of the most favorable environments for it? Over time, however, the planet's chemical signatures began shifting in a troubling direction. Clay minerals became less common, while sulfates started appearing more frequently. Minerals associated with acidic environments, sulfur-rich waters, and intense evaporation. Acidic conditions make complex chemistry far more difficult and are significantly less hospitable to stable organic compounds. While life on Earth can survive in acidic environments, it tends to become highly specialized and far more limited. Then there are the carbonates. In theory, if Mars once possessed a thick carbon dioxide atmosphere alongside stable liquid water, carbonate minerals should be widespread, much like they are on Earth. Instead, carbonates on Mars are surprisingly rare and localized, appearing only in a handful of regions such as Nili Fosse. This scarcity may be a critical clue. It suggests that the Martian climate system did not regulate itself the way Earth's does, and that Mars may have lacked the long-term stability needed to sustain habitable conditions for geological timescales. But minerals only reveal the environmental conditions. To understand how water actually behaved on Mars, we must examine the places where flowing water carved its story directly into the landscape. Among the strongest pieces of evidence are the valley networks covering large portions of the southern hemisphere. Viewed from orbit, their appearance is unmistakable. Branching drainage systems where small tributaries merge into larger channels, remarkably similar to river systems formed by long-term rainfall erosion on Earth. Geometric analyses indicate that these structures were shaped by slow, repeated erosion from persistent water flow over extended periods. Hydrological models suggest that forming valley systems of this scale and density would have required precipitation or surface runoff lasting at least hundreds of thousands of years, and in some regions, possibly several million. All of this points toward one unavoidable conclusion. Liquid water on ancient Mars was not a brief anomaly or an isolated event. Jezero crater offers an even more refined yet highly persuasive piece of evidence. Stretching roughly 45 kilometers across, the crater once hosted an ancient lake. One of its most remarkable features is the fan-shaped delta along the western rim. The sedimentary layers inside it show a gradual decrease in grain size from bottom to top, a classic sign of material settling in calm or slow-moving water. On Earth, formations like these develop over thousands, sometimes tens of thousands, of years as rivers continuously carry sediments into lakes or shallow seas. Data collected by the Perseverance rover confirms that the rock layers inside Jezero display sedimentary characteristics associated with long-lasting aquatic environments rather than sudden, catastrophic floods. That is precisely why Jezero became the primary target in the search for ancient biosignatures on Mars. Closer to the Martian equator lies Gale Crater, an enormous basin measuring about 154 kilometers in diameter. Rising from its center is Mount Sharp, also known as Aeolus Mons, towering nearly 5 kilometers high. Unlike volcanic peaks or tectonic uplifts, this mountain is essentially a massive stack of sedimentary deposits accumulated over immense spans of time. Research conducted by the Curiosity rover revealed that many of these layers formed in ancient lake environments that experienced recurring cycles of wet and dry conditions. Considering the thickness of the deposits and the estimated rate at which they accumulated, the lake inside Gale Crater may have persisted for millions of years, long enough for complex chemical reactions to take place. Taken together, these discoveries point toward a striking conclusion. Ancient Mars sustained an active and persistent water cycle for extremely long periods. And if liquid water remained stable for that long, if rivers and lakes survived for millions of years, an unavoidable question emerges. Could Mars once have possessed an ocean, particularly across its northern hemisphere? The hypothesis of a northern Martian ocean begins with a simple yet intriguing observation: the dramatic contrast in elevation between the planet's two hemispheres. On average, the northern hemisphere sits 4 to 5 kilometers lower than the southern highlands, forming a vast depression known as the northern lowlands. On Earth, elevation differences of that magnitude are commonly associated with ocean basins. Several topographic maps created using data from the Mars Global Surveyor and Mars Reconnaissance Orbiter reveal winding boundaries stretching for thousands of kilometers that resemble ancient shorelines. According to various models, if such an ocean truly existed, it may have covered between 20% and 30% of Mars' surface and contained enough water to create a global layer several hundred meters deep. This is where the debate becomes far more complicated. Unlike coastlines on Earth, the proposed Martian shorelines are not level. Their uneven elevations have led many scientists to question whether they are genuine oceanic remnants or instead the result of erosion, crustal deformation, or other geological processes. The situation becomes even more difficult because of Mars's volcanic history. Over billions of years, enormous lava flows spread across the northern hemisphere, potentially burying ancient terrain, obscuring water-related features, and distorting older geological evidence. Another theory suggests that the northern lowlands were not carved by water at all, but instead formed after a colossal impact early in Mars's history. An impact of that scale could have created the hemispheric imbalance first, with water and climate processes later occupying the basin temporarily. In that scenario, any ocean that existed would have been a consequence of the structure, not its original cause. Even so, global water balance models indicate that the amount of water required to produce all the observed rivers, lakes, and sedimentary formations is immense. If water existed only in isolated local basins, explaining a long-term planetary water cycle becomes significantly harder. At present, there is still no definitive consensus that Mars once possessed a global Earth-like ocean. However, the possibility of enormous bodies of water, perhaps shallow seas appearing during certain phases of the Noachian or early Hesperian eras, remains scientifically plausible. For such oceans or seas to survive, ancient Mars would have required a climate warm and stable enough to support them, which leads directly to the next mystery. How did Mars retain its heat? Climate simulations suggest that during the Noachian era, Mars may have possessed an atmosphere rich in carbon dioxide and water vapor, two critical greenhouse gases. If atmospheric pressure reached several hundred millibars or more, CO2 could have trapped enough heat to keep surface temperatures near or even above the freezing point of water. Yet carbon dioxide alone was likely insufficient. Advanced three-dimensional climate models indicate that even a thick CO2 atmosphere struggled to maintain globally stable temperatures above 0 degrees Celsius on early Mars. This led scientists to propose that the greenhouse effect must have been amplified by additional factors, secondary greenhouse gases that may have played a subtle yet crucial role in stabilizing the planet's climate. One of the most compelling candidates is hydrogen. In a dense Martian atmosphere, collisions between hydrogen molecules and carbon dioxide could have generated an additional greenhouse effect far more powerful than CO2 alone. Modern climate simulations suggest that even a relatively small concentration of hydrogen in the atmosphere might have increased surface temperatures by dozens of degrees Celsius. However, hydrogen is extremely light and escapes easily into space. For ancient Mars to maintain meaningful amounts of it, the planet would have required a constant source of replenishment. This is where volcanism becomes a critical part of the story. During the early stages of Martian history, intense volcanic activity may have released not only carbon dioxide and water vapor, but also hydrogen and methane. Although these gases would not remain stable for long periods, they could have produced temporary climatic warming phases, intervals during which temperatures rose enough for ice to melt, rivers to flow, and lakes to persist across the surface. From this perspective, early Mars may not have been continuously warm like Earth. Instead, its climate likely shifted between warmer and colder eras, creating an unstable but periodically habitable world. Another factor that is often underestimated is the role of dust and clouds. Even on modern Mars, dust can either cool or warm the planet depending on atmospheric conditions. In the thicker atmosphere of ancient Mars, clouds composed of water ice or carbon dioxide crystals may have acted like thermal insulation, trapping infrared radiation and redirecting heat back toward the surface. Some climate models suggest that clouds positioned at certain altitudes could have played a major role in maintaining warmer temperatures, although this mechanism remains heavily debated. Taken together, these hypotheses point toward an important conclusion. The climate of ancient Mars was not simple, stable, or predictable. It was most likely the product of a delicate balance between multiple interconnected systems: atmospheric composition, volcanic activity, greenhouse gases, cloud dynamics, and even the planet's orbital variations. And if conditions once allowed liquid water and energy sources to coexist, another question naturally follows. Could life have taken advantage of that opportunity? From a biological standpoint, the minimum requirements for life on ancient Mars may indeed have existed. Liquid water was present for extended periods. Energy could have come from sunlight, chemical interactions between water and rock, or hydrothermal systems beneath the surface. The essential ingredients for biology, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, have all been identified within the Martian crust. But habitable conditions are not the same thing as confirmed life. That distinction remains one of the most important boundaries in planetary science. At present, there is still no direct evidence that Mars was ever inhabited by living organisms. No fossils have been discovered, no preserved microbial cells have been found, no unquestionable biosignatures have yet been identified. Still, if life did emerge on Mars, the most plausible form would likely have been simple microorganisms resembling the bacteria or archaea that existed on early Earth. Such organisms would not require oxygen-rich atmospheres or complex ecosystems. They could have survived within sediments beneath shallow water or deep underground, shielded from radiation and protected from the planet's increasingly unstable climate. On Earth today, similar microorganisms continue to thrive in some of the harshest environments imaginable, from hydrothermal vents at the bottom of the oceans to rocks buried kilometers beneath the surface. That is precisely why modern Mars missions focus so intensely on the search for ancient biosignatures, indirect traces that life may once have existed there. The Perseverance rover was designed specifically for this purpose. It drills into rocks, collects and stores samples of sedimentary material inside Jezero crater, an environment that was once rich in water and potentially capable of preserving biological evidence. Its scientific instruments analyze rock textures, organic compounds, and chemical relationships that could point toward ancient biological activity. All of this highlights a deeper reality about life itself. Life appears to be fragile, not inevitable. Even when the initial conditions seem favorable, biology may never emerge at all, or it may arise briefly, only to disappear long before a planet can preserve any lasting trace of its existence. Mars may simply have had a window of habitability that was far too brief. Once its climate began to deteriorate and liquid water became scarce, any emerging biosphere, if it ever existed at all, could have vanished without leaving clear or lasting traces in the geological record. Earth had decisive advantages: a larger size, a strong global magnetic field, active plate tectonics, and a long-term climate cycle sustained over billions of years. Mars had none of these stabilizing systems. It may have offered the initial conditions for life, but it was unable to preserve them for long enough. So, what transformed Mars from a potentially habitable world into the barren planet we observe today? In its early history, Mars likely possessed a global magnetic field generated by a core dynamo, operating in a manner broadly similar to Earth's. As long as its molten metallic core remained hot enough for vigorous convection, it sustained electric currents that produced a protective magnetic envelope around the planet. However, Mars is significantly smaller than Earth, roughly half its diameter and just over 10% of its mass. This smaller size led to faster heat loss. As the core gradually cooled, convection weakened, the dynamo slowed, and eventually shut down entirely. With it, the planet's magnetic shield disappeared. From that moment on, Mars was exposed directly to the full force of the solar wind, no longer protected by a global magnetosphere capable of deflecting high-energy charged particles. The upper atmosphere began to erode under continuous bombardment from the sun. Light gases such as hydrogen and oxygen were ionized, stripped away, and slowly carried off into space. This was not a sudden collapse, but an extremely gradual process that unfolded over billions of years. NASA's MAVEN mission has provided direct evidence of this atmospheric loss. Measurements show that after the magnetic field weakened, solar wind and intense ultraviolet radiation began actively stripping away the Martian atmosphere, with escape rates in the past likely much higher than those observed today. An atmosphere is more than just air. It is a planet's thermal shield. Once it becomes thin, surface pressure drops. Liquid water becomes unstable, and the entire climate and geochemical system begins to unravel. The magnetic field was a key factor that allowed Mars to retain both heat and water. Earth had it, Mars did not, and that difference ultimately determined two entirely different planetary fates. As the protective field faded, the atmosphere thinned further, temperatures declined, and water either froze or sublimated into space. Once pressure fell below a critical threshold, rivers and lakes disappeared, the hydrological cycle collapsed, and the planet lost its ability to regulate climate. Today, most Martian water exists only as ice, inactive and unable to sustain the dynamic processes that define a living world. In this way, Mars transitioned from an active, evolving planet into a cold and nearly inert desert, the collapse of an interconnected planetary system. Earth, in contrast, endured climatic catastrophes, but recovered repeatedly thanks to its size, magnetic protection, and tectonic recycling. Despite their similar beginnings, shared formation processes, volcanism, and abundant water, the decisive factor was scale. Earth managed to preserve the conditions for life. Mars did not. This suggests a fundamental truth. Life is not enough to simply emerge. It must also be continuously protected. Ancient Mars once had a thick atmosphere and flowing water, but the cooling of its core and the loss of its magnetic field opened the door to solar wind erosion that gradually stripped the planet bare. Its story is a lesson in planetary evolution. Life can persist only where long-term protective mechanisms remain active. Mars is therefore not just a dead world. It is a possible future scenario of what Earth could have become. And at the same time, it stands as a stark reminder of how fragile our own planet truly is.